are. All right. Okay, so let me share my screen again. Okay. Let me pull this up. Okay, so let's talk about the project you guys will be working on your groups. Basically, we want you to code two kinds of matrix inverting functions. They will be the two kinds of algorithms that you'll be using is the Gaussian elimination and the LU decomposition. So those are two different ways of inverting a matrix, but basically you will end up with these two inverters, and you will use them on a practical project that we've designed. So for a little bit of context, I know that not all of you have taken a linear algebra class before. So as a little bit of context, if we have a system of equations with different variables, such as this, like these three equations hold true at the same time, something on x and y and z equals something else. These three equations and three unknowns, we can. Hello?
Jose?
Yeah.
I'm so sorry to bother you, but I can't join the breakout room. Do you mind assigning me to the first breakout room?
Of course, just 1 second.
Me too. Could you add me into the breakout room, please?
Yeah, actually, I wanted to join, but I.
Yeah. Just 1 second. I'm sorry about that.
Thank you.
So. Wait,
I'm sorry, I just joined. What's the breakout room for?
Discussing lab 12. The breakout room is for discussing lab 12.
Okay, got it.
I'm trying to assign you to the breakout room. I'm just not sure why I don't have that option. Oh, I think Dan is still the administrator of the. Wait, let me pause the recording. Okay, so we're back. Sorry about that. We had a few technical difficulties so far. Anyways, as I was telling you, if you have a set of three or more equations that need to hold true all at the same time, such as this one, you can express that as a matrix multiplication of the type that we have down here, with a matrix of coefficients times the variables x, y, z equals something, some constant. So this is equivalent to saying 3 times x plus 7 times y plus 1 times z equals 5, which is the first equation we have here. 0x, we have no contribution of x in the second equation, minus 2 times y plus 4 times z equals 15. That's the second equation. So minus 2y plus 4z equals 15, and you get the gist of it. So for such a system of equations to have a solution, we need a few things to hold true. This system of equations could either have a single solution or an infinite amount of solutions. And we'll get to that later. But for now, let's just assume that a solution exists. There is some set of x, y, and z that makes all these equations hold true at the same time. And this can be generalized to bigger sets of equations. Like if we call all the variables x1, x2, all the way to xn, instead of x, y, and z, we could have like x1, x2, and x3 times some kind of coefficients, a11, a12, a1j, all the way to a1n equals some constant b. So here we have a set of m equations. If you see, we have m rows, 1, 2, all the way through m, on n variables. So we have x1, x2, all the way through n. So for such a system of equations, we can write it again as a matrix form of the type A, which is a matrix of coefficients, times x, which is the vector that contains all the variables, x1 all the way through n, which could be again like x, y, z, but if we could have many more variables than only 3, equals some vector b of just constants. All right. So if we have a system that has the same amount of equations as the amount of variables, so n equals m, the two solution methods that we will work on this project are Gaussian elimination and LU decomposition. So this is important. It has to be A has to be a square matrix. M has to be equal to n. So if we have 10 equations, we have 10 unknowns. If we have 20 unknowns, we need 20 equations. Okay. So for Gauss elimination, what we do is apply a set of operators to the matrix. So these are called Gaussian operators, valid Gaussian operators. And these are, so what we are allowed to do is to either swap the order of 2 rows. We can multiply a row by a constant that's not 0. Like we could multiply some row by 2 that's valid, that doesn't change the inverse of our matrix. And we can add a row to another one, or we could add a multiple of a row to another one, as long as we're not multiplying by 0. So these are the 3 valid operations. Exchange, swap one row with another one, multiply one row by any constant that's not 0, and add a multiple of a row to another one. So these 3 operations, like for us as humans, it's really easy to do them. It's very easy for us to grab a matrix and and say, okay, I will just multiply all the first row by 2. And we as humans can do that really easily. It's not a complicated task. But you get to wonder, how can I code these efficiently? So these 3 operations are equivalent to writing these matrix operations that we will see right now. Let's say that we want to swap. So basically, to build these matrices, you basically start with the identity matrix and do the change that you want to do, and then you got your transformation matrix. So that's a really nice, really convenient way to remember how to build these transformation matrices. So let's say, for example, that we have a 3 by 3 matrix, or matrix A, if you remember from before, and we want to swap the second and third rows. So if we take the identity matrix and do exactly that, swap rows 2 and 3, we get this guy here, or transformation matrix. So if we multiply this matrix times whatever matrix we have, times our matrix A, that's also 3 by 3, then our result will be the matrix A with the rows 2 and 3 swapped. And in a more general case, so look at the nomenclature we're using here for T, that's for transformation 2, 3, which means exchange rows 2 and 3. We have this guy. So for T, Ji, which means exchange rows J and I, we have a matrix like this. That's ones in the diagonal, so basically the identity matrix, except for rows I and J, which have been exchanged like this. Okay. Feel free to stop me at any point if you have any questions. I'll stop right now for a few seconds to see if anyone is okay so far. Okay, so if there are no questions so far, let's keep going. Sorry, I mixed my slides. Okay, so the other operation, the other valid operation we can do in Gauss elimination is to multiply a row, any given row, by a non-zero constant. So again, to do that, so let's say we have a 3x3 matrix and we want to multiply the third row by 7. The transformation matrix we need, we will get it by applying that operation to the identity matrix. So if we have the identity matrix of 3x3 here, the transformation matrix we want is multiplying the third row of the identity by 7. So you can see that here. And again, look at the nomenclature we have. T of 3, that's the transformation of row 3, parenthesis 7. So this nomenclature we are using, this is specific to this project, like it doesn't come from anywhere else. So what this means is multiply row 3 by 7. And again, more generally, so TI of C, that means multiply the ith row by C. So it will be essentially the identity matrix except for the ith element, which is the number C. All right. And finally, our third operation, which was adding a multiple of one row to another. Again, we apply this transformation to the identity matrix to obtain the transformation matrix. So again, let's say we have a 3x3 and we want to multiply the second row by -2 and add it to the first row, or basically subtract twice the second row from the first row. So we apply that to the identity matrix. So the first row, which is 1, 0, 0, plus -2 times the second row. So -2 times 0, -2 times 1, which is the second element of second row, -2 times 0. And we end up with this guy. This is our transformation matrix. If we pre-multiply a 3x3 by this, our result will be the same matrix, but with the first row, that will be now the first row minus twice the second row. And the nomenclature we use is T to 1 minus 2. So in here, the order matters because it is not the same to add -2 times the second row to the first row than the opposite, adding -2 times the first row to the second row. These are not the same. So here the nomenclature means row 2 times -2 plus row 1. Okay. So again, if we generalize this, we will have an identity matrix with ones in its diagonal, but on the, so if we want to add C times row I to row J, we will replace the, or not replace, we will change the ith row to a C on the Jth position. So pay close attention to the indices here. So this means that the diagonal is of ones, but in row I, we have a C, And where exactly in row I, if we see this column matches this one, and since this is the diagonal, this one is on the jth row and the jth column, so this C is on the jth column of the ith row. Okay, pay close attention to the indices. You will have this presentation while you're working on your project, so you can look at it closely and you can work out the math by yourself. But once again, this means adding C times the ith row to the jth row. Okay. I'm gonna stop again for a few seconds to see if there are any questions. And let me check the chat too. I actually lost the chat. So, okay, I cannot see the chat for some reason. So if you have any questions, please speak up. Okay. So now the proper algorithm of the Gauss elimination. It's divided on two phases: forward elimination and back substitution. So we will go through both. During the forward elimination, we are trying to use these these three value transformations that we mentioned to turn our matrix into an upper diagonal matrix. So we want to take our A matrix with all the coefficients and use these operations such that everything below the diagonal will be zeros. All right. So to do that, for each of the first n-1 columns, so remember that this is an n by n, so for the first, for all the columns before the last one, we're calling them Cj. We want to eliminate all the components Aij below the Ajj diagonal, where I equals j plus 1 through n. So again, for the first column, we want to eliminate, so the first column, so j will be equal to 1. We want to eliminate all the rows, all the elements in rows I that are j plus 1, so 2 through n. So this element all the way through the end, we want to eliminate it. Second column, the same thing. Everything below the diagonal, so what would be the third element that's inside these ellipses, all the way through the end should be brought down to zeros. So here we show you the operation that we need for that. So we are adding Tij of negative Aij over Ajj. So, okay, these the indices are tricky, but what this means, and you'll need to look at this slowly and convince yourself. What this means is that, actually, I think we have an example rather than go through it just symbolically. Okay, we'll go through an example later. Basically, the goal of the first stage is to get this upper triangular matrix. Okay, then we go to the second stage, which is back substitution. That is solving for each variable from bottom up. So here's a formal mathematical expression for that. Again, I think it's better for you to go home and look at it more slowly. We'll go through an example here to make this a little bit more clear. So here we are back at the system of equations we proposed in the first slide. And in matrix form, if you recall, it looks like this. So these are our x1, x2, and x3. So or variables or unknowns, or in this case, since there are only three, x, y, and z. So we will go column through column, and we want to eliminate all the coefficients below the diagonal. So for column J equals 1, and for rows, so here I am almost giving you a little bit of a pseudocode, because these will be two loops, one inside each other. So one for the columns and one for the rows. So for the column J equals 1, and for the rows I equals J plus 1 through n. So in this case, 2 and 3. Again, everything below the diagonal. So let me jump back for a second. First column, this guy. Rows 2 and 3, this and this. We want to turn them to 0. So for the first of those rows, I equals 2, we take the transformation Tij of the elements negative Aij over Ajj to row I, and we will go through that more slowly below, minus, sorry. This, so this transformation means row I minus Aij over Ajj of row J, and assign that to row I. That's how you read this. So what do I mean by this? I am going to multiply. So let's not look at this item because this one is already 0. Let's look at this one, which is more interesting. To turn this guy into 0, I have to subtract this guy, which we know that it's not 0 on the diagonal, multiply by something. And that something is the ratio between this guy and this guy. All right. So in this case, both values are 3. So if I subtract this row, multiply by 1, so the ratio is 1 in this case. If I subtract this row from this row, I will get a 0 here. All right. So this is what I mean. This is what it means. For the row we want to turn to 0, the ith row, we subtract a multiple of the jth row. And the jth, and remember we are on the jth column. Okay. So this is, let me see. Okay, so here I'm just going that the second row already has a 0. So if we apply this to eliminate the first element of this second row, it's already a 0, so nothing changes. But if we go to row 3, so we will want row 3 minus this ratio, which is 1 in this case, of row 1, that's applied to row 3. And if you see here, the first term, the x term, disappears. It goes to 0. Then we go to the second column, j equals 2. And we want the rows below the diagonal. Since it's just 3 by 3, the only row is row 3. So we want to have row 3 minus this ratio of row 2 assigned to row 3, such that row 3 has an element that disappears. Okay, so what is this ratio? 832 over 822. Let's go back for a second. 832, that's row 3, column 2, it's this guy, -9 over 822. So row 2, column 2, that's this guy, -2. So row 3 minus 9 over 2 of row 2 assigned to row 3. So this is what we got here, and the second element disappears. If we write it in matrix form, it looks like this. Yeah, so we see that all the terms below the diagonal, they have gone to 0. Again, there is a very almost self-evident logic on why this happens. So going back to this point, here we have -9 on the second element, and we want to eliminate the second element by adding something. So if I add the first something times the first row to make this guy disappear, we have a problem because the first row has an element on X. So we might make the Y go to 0, but there will be something in X, and it will not be upper triangular. We want everything below the diagonal to be 0, so we don't want an X on this row. So we see that we can use row 2 because it doesn't have an element on X. We will not be contaminating or third row with something on X. So we have to add row 2 times something to bring this to 0. So the easiest way to do that is that to multiply row 2 by 9/2, because this by -9/2, because that will make this guy turn into +9. So we will have a +9 minus 9. This guy goes to 0. X remains 0, and Z, something happens to Z and to B. We don't really care. By the way, all these transformations are being applied to both the left and right hand side of the equation. Yeah, so if we here we will add something that makes the Y 9, it will make this Z into something else, 4 times 9/2, and the 15 will also be 15 times 9/2 plus -5. So we end up with this matrix of coefficients and this vector at the end. Okay. So this is the end of the first stage because we have the upper diagonal matrix. So that is the forward elimination part of the Gauss elimination algorithm. Then we go to the backward substitution. So the backward substitution makes use of the fact that we have a lower diagonal matrix, because so backward substitution means solving for the variables from the bottom to the top. Why? Because we have this row that's super nice and pretty that simply says that -20 times Z equals this guy. So -20 times Z equals this guy. So we can solve for Z. Z equals this guy over -20. Excuse me for a second. Let me just reply something. Okay, sorry about that. So for the last row, we basically have Z. And then we go to the second to last row. Here we already know Z. So we have -2y, we don't know y, plus 4 times Z, we do know Z. So whatever number we have here equals 15. So y equals 15 minus 4 times whatever we got from this guy over -2. All that over -2. And we get y. Now we go to the previous row. We know y, we know Z. So we only have one variable to solve for, which is really easy. We move everything to the right side and we divide everything by 3. So that's what backward substitution does. So the way to express that mathematically and actually coded is that for all xi, again, I am here giving you a little bit of a pseudocode, so it will be a loop over I equals n colon -1, so going down all the way to 1, so 3, 2, 1. We will start with the first one, I equals 3. So xi, so third variable, in this case, or z, equals 1 over aii. aii is the coefficient of that variable, so in this case is the -20 of bi, the constant of that equation, of that particular equation, minus the summation of j equals I plus 1 through n. So in this case, j equals oh well, actually so this is the general expression, but if you look, since we are in the last row, the j equals I plus 1 doesn't really make sense. This would be a 4, and we don't have a fourth column or row. So you will have to make a special case for the last row, not necessarily third, it could be much bigger, but for the last row. So for that particular case, this guy equals 0. Yeah, so if we substitute the values down here, we have a summation from j equals 4 to 3. That doesn't really make sense. So for that special case, this guy is 0. So it's only 1 over 20 times the bi, this guy, negative 145 over 2. So we get a value for z. Again, we are inside this loop for all xi, for I equals this, 3, 2, 1. So we go to, so this is the state of our matrix right now. We already know z. This guy is already known. So we go to the previous row, I equals 2. We have the same expression as before, and now the summation actually makes sense. So we have x2, that's our second variable, or y, equals 1 over aii, the coefficient of y. So -2, 1 over -2, times bi, that's the constant of that equation, 15, minus the summation of j equals 3 to 3, so just j equals 3, of aij, I equals 2 in this case, and j equals 3. So row 2, column 3, this coefficient 4 times xj. So xj is the next variable, the one that we solved already, the one of the next column, row. So z, xj, j equals 3, so third variable. We already have that. We substitute that. So -1 over 2 times 15 minus 4 times z. All right, so that's exactly the same operation we described before. Let me see. There's a question in the chat. Will we be given a written document specifying what we need to do for the project, or will it only be told to us verbally? You will have the recording of this presentation. You will have this presentation that we are looking at in a PDF. It's on B courses right now. And you will have a PDF describing the application that you need to, for which you will use the function that you build here. Okay, so moving on to the first row. So from this guy, sorry, I went back. From this guy, we have y, we have the value for y. And we go to the first row, we know y and we know z. So we solve for x. So again, same expression as before. X equals 1 over this coefficient, 1 over 3, times 5 minus the summation of 7 times the value of y we already know, plus 1 times the value of z that we already know. Okay, so we have the numbers down here. X equals this guy, and we have solved our system of equations. So all these coefficients times x equals this, y equals this, z equals this, equals all these coefficients. And we have solved our equations. There is one very important caveat on this algorithm, something that can go wrong. And it is what happens if we divide by AJJ if AJJ is 0. Because when we were doing the forward substitution, and sorry, not forward substitution. The forward, when we were doing the forward elimination, we were dividing things by AJJ. And if that's a 0, if there's a 0 on that diagonal, then that's divided by 0. It goes to infinity, and we cannot continue. So the way to solve this is called pivoting. So what we do is that we always find the component with the largest absolute value in the current column, in the jth column, and swap it to the jth row. So what do I mean by this? So in the examples we were looking at before, there was not a 0 on the diagonal, so we did not run into this issue. But in a general case, you will want to pivot before starting forward elimination. So if we look at column 2, in this example here, if we go, we already made forward elimination on column 1. If you see, there is no value for the x's in rows 2 and 3. So those are already 0. We go to column j equals 2. And we find the largest absolute value in that column, which is 9 in this case, and swap it to the jth row. So we swap it such that this 9 is in the diagonal. Okay. And also remember that we are doing, in forward elimination, we are looking for an upper triangular matrix. We want everything below the diagonal to be 0. So we only look for the largest absolute value in the current row downwards. We don't want to, like, if this guy was a 17 instead of a 7, it would be the largest absolute value of that column, but we don't want to swap it to the second place, to the diagonal, because it would carry a value in x with it, and we wanted to eliminate the x's below the diagonal. Okay, so be careful with that. So you will need to do pivoting before starting forward elimination for each column. Okay. Any questions on the Gaussian elimination before we discuss LU decomposition? Okay, I think we are fine for now. So LU decomposition starts from the fact that you can decompose every matrix into a lower triangular times an upper triangular matrix, right? So if we have a matrix A of all these coefficients, we can decompose it into a lower triangular L times an upper triangular U. So L times U. And again, upper and lower triangular mean that for lower triangular, we have values for everything below the diagonal and the rest is 0. Upper triangular, we have values on everything above the diagonal, everything else is 0. So for the equations we had before, ax equals b, we can decompose it into ax equals lux. So a equals lu, so lux, which equals ly. So if we say that ux equals y, so ly equals b. So why do we care for this? Because you saw how easy it was to do the back substitution once we had the upper diagonal matrix, right? So the last row basically means this equals some number divided by another one. Then we know that variable, we can solve for the second to last. Then we know those two and we can solve for the previous one. So that's really easy. That's really easy. So we could express the problem we have as an L times some y equals b, and that will have the opposite form. So we could solve for the first row, which is easy. So it will be the first variable equals something over something. Then we know the first one, we can solve for the second one. We know the first two, we can solve for the third one, and so on. So instead of backward substitution, forward substitution. And we can solve for the y's. And then we don't really care for the y's. These y's are a set of temporary variables we devised to make our life simpler. But we have an equation ux equals y. We define that to be that way. And these will be an upper triangular matrix. So we could do back substitution. So we will basically do forward substitution first for the temporary variables, and then backward substitution for the real variables. Okay. So the first question you will probably have is, how do we actually split the matrix into L and U, into the lower and upper triangulars? So just by convention, we will choose the L to be once on its diagonals. And well, that's it. That's the assumption we will make, to be that L is once on its diagonals, to make this problem easy to solve. So again, when you do matrix multiplication, the indices are a mess, but this basically says that for any element ij, that will be the same as the ith row of the L matrix times the kth column of the U matrix. You dot multiply those, and yeah, that gives you the original aij, so whatever value you had in the original matrix. So we basically solve for each of those. So we again look at this as a pseudocode in a sense. You have a for loop that goes for columns j equals 1, 2, and 3, and you have an I loop that goes for rows 1, 2, and 3. So 1 through n, whatever's the size of the matrix. So excuse me. So we basically are going to be solving for the elements of U and L column by column. So in the first column, the only element in U will be U11, right? If we go back one slide, we're on the first column. So we only care about U11. We know the rest are 0. And we care about L2 2, 1, and 3, 1. So this guy and this guy, because we know the one on the diagonal is 1. So we have these expressions for those. You can derive those at home if you want to. Look at them closely. These are very generalizable. We go to column 2. Again, U has 2 elements on that column. U 1, 2, and 2, 2. L has also 2 elements. L 2, 2, which we know it's 1. It's the one on the diagonal, and L 3, 2. And again, in case anyone's lost with the notation, these subindices mean row then column, right? Just exactly as we've done in MATLAB so far in programming. And same idea for row 3. In this case, we don't have any elements in L that we care for. We only have the last element of the diagonal. So going back, so this guy, which already know is 1, and we have all the elements in U. All right, so here you have these expressions. You have a general equation before that you will have to look at closely. It's not so bad as it looks like. It looks pretty intimidating. Don't worry, it's just a summation. But yeah, I won't go too deep into that because I think it's better for you to look at it at home. At the end of the day, what you need to code are basically these 2 expressions. Because yeah, this process, the example from before, that's for a 3x3, but we want to be able to solve as whatever size we have. So this is the general expression to solve for the U's and the general expression to solve for the L's. Remember, we will gonna go on a for loop through the columns J. So J equals 1, we solve for the rows I. J equals 2, we solve for the rows I, so on and so forth. And inside each column, we will have this expression for U for I equals 1 through J, because remember, U is the upper diagonal, so we want for everything before the diagonal. And for L, we will have I equals J through N. Okay, so L is the lower diagonal. We care for everything below the diagonal. So these are the expressions that you'll need to code for this. Here's an example. I think it's the same matrix as before. Yes, the same matrix as before. So we go for the first column. In the U's, we go through from I equals 1 through J. So in this case, J is equals 1. So we only care for the first element of U, U1, 1, equals just this coefficient. And for L, we care for everything below the diagonal. So L2 and 3. And yeah, this is just algebra. For column 2, again, U is I equals 1 through J. So everything above the diagonal. L equals 3, everything below the diagonal. Same idea for column 3. And doing all that, we get these 2 matrices, this guy and this guy. This guy is lower diagonal, this guy is upper diagonal. So then we solve for our fictitious or temporary variables y, as we said. So we have, instead of ax equals b, we have lu times x equals b. And instead of lux, we have ly equals b. So y is ux. You can go to the previous slides to look at this more slowly. So we have L times some dummy variables y equals B. We do forward substitution. So the first row, that's direct. Y equals 5 over 1. Second row, that's 15 minus whatever was, in this case, 0 over 1. So J2 equals 15. And J3 equals 0 minus 1 times J1 minus 4.5 times J2. And we get our value for J3. So we have our dummy variables J. And then we know that J equals UX. We have that from before. So this is just as in the backward substitution from the previous algorithm. We can see directly that X3 equals this guy over -20. So, and again, our X3, that's our third variable, or Z in this case. So this guy over this, we got that. We go to the previous row. We already know Z. So Y equals this guy minus 4 times Z, which we already know, over -2. So it's this expression here. We know Y and we know Z. We go to the previous row and we solve for X. And that is the end of it. That's the end of it. That's all that there is for LU decomposition. We build those two matrices, L and U, and then we use the forward substitution and backward substitution, which are really simple algorithms. So at the end of this, you will have two functions. One will be my Gauss solver, which will use the first algorithm we'll look at. And the other will be my LU solver, which uses the second algorithm, the LU decomposition. Excuse me. Okay. Do we have any questions so far? I realize that this is a lot. Share another document with you. Again, this recording will be available for you guys to look at later on. And we will also have a lab on Wednesday to go over this again. Yes, let me find. Okay, this guy. So at the end of this, you will have those two functions, my Gauss solver and my LU solver, which can be used to invert matrices. And inverting matrices has many applications in engineering. So the application we want you to work on using these two solvers. Let me share my screen. Sorry, I think I'm sharing the wrong screen. Actually, I don't know what I'm sharing. Can you guys see the PDF? I'm not sure what I'm sharing. Okay, I hope you guys can see the PDF. Okay, so what we want you guys to do is to apply these to be able to describe the orbit of a planet. Okay, so we will be providing you with two data files, x coordinates and y coordinates. Those are a set of coordinates that describe the position of planet Mars in millions of kilometers. Okay, and we know from physics that planets should describe elliptical orbits, right? But you will discover if you plot these coordinates that they do not actually describe a perfect ellipse. Why? Because there is noise in our measurements. So these are measured positions, and as you will find in many engineering and science applications, you'll measure data will have noise because our instruments are not perfect, because our measurements, like the us as human beings making the measurements cannot make it perfect, can do it perfectly. Um, Maybe there are conditions that we are not considering. For example, in this case, that it's the location of planet Mars. That's really far away, and maybe we're measuring something with a telescope, and there might be atmospheric conditions bringing noise into our measurements. There might be deviations from our models. Our models are very idealistic. They simplify a lot of things. So if you have two celestial bodies orbiting each other, they will do it in an elliptical manner. But in a planet, it's not true that that's only the planet and the sun that are interacting. The planet and its moon, they are orbiting each other. So probably the actual location of the planet will be a little bit wiggly. So there are many sources of noise to the data. So if we actually tell a computer, feed an ellipse through all of these points, it will not be able to do it. There is no ellipse that will actually be able to go through all of the points because they are noisy. There are random noise. There's random noise. There's random contamination. So it's you may wonder, okay, what do we know? What can we generalize? An ellipse in a very general sense can be expressed as we can see on this equation. So something times x squared plus something times y squared plus something times xy plus something times x plus something times y equals 1. So that's the general equation for an ellipse. So and here the w's, these are coefficients that we don't know that describe some ellipse. Excuse me. So you can interpret this as a linear combination of the polynomials x squared, y squared, xy, x, and y. Yeah, so what I mean by a linear combination is just what I said before. Something times this plus something times this plus something times this, etc. So we could actually put all these polynomials, these polynomial features into a matrix like this. So for these are the x's, and for each row represents 1 point. So the first point, x comma y, here's the x squared, y squared, x and y for the first point. The second row is the same for the second point, and all the way through the last point, n, which in this case it's like 1600 or something like that. So if these guys actually described an ellipse, a perfect ellipse, then we could write this matrix times our weights equals 1, like the vectors of ones, right? So this will essentially mean that we have n equations, and all of the n equations have this form from above: something x squared plus something y squared, etc., equals 1. We will have n equations that hold this true. The problem is that our 1600 data points, they don't describe an ellipse exactly. So we don't actually know which ellipse they try to describe. So we don't know the weights W. But let's assume we know the weights W. We know that all of these equations will be slightly off. They won't really be one because of the noise. They would be close to be true, but not quite. So we will. So the best we can do is to try to find an ellipse, the ellipse that most closely matches all of the points. It will not be able to be we will not be able to find an ellipse that goes through all of the points, but we can find the closest ellipse that does that. Okay. So this is a minimization problem. We don't expect you to go through all minimization theory. We give you the formulas, but the minimization is we want the difference between, so our equation, the ideal ellipse is phi times W equals 1. So we want the difference of phi times W and 1 to be as low as possible. All right, so we want phi times W. We cannot make it equal 1, but we want all our phi times W's to be as close as 1 as we can. So that is our problem posed right here in this formula. And the way to do it is, so the solution here, we want to find the W that describes the best ellipse. We are trying to find the best ellipse. That means finding the weights W for the equation we saw before. So that the best W is the one described in here. Phi transpose times phi, all that inverse, and we just developed two functions to calculate this inverse. That times phi transpose, and that times the vector of ones. Okay, so that will give us our W's. So that's all. That's the context of the application. Now, what we actually want you to do in this project. So this operation, phi transpose times phi, all that inverse times phi transpose, that is called the Moore-Penrose pseudo-inverse of phi. In case you're curious, there's articles in Wikipedia about it and about what it does. But it's basically the best way to solve these problems where we cannot really solve a set of equations like we had before. We cannot really have all the equations hold true, but we want them to hold as close to true as possible. So the pseudo inverse is great for that. So we want you to use your Gauss solver and your LU solver to calculate the pseudo inverse of phi. With the pseudo inverse.
Quick question: are we not allowing people? Hold it. Say.
Yeah.
I was wondering, the Moore-Penrose pseudo inverse is P inverse, that function. Are we not allowing students to use P inverse?
No. They're not allowed to use P inverse or
Okay.
any of the other matrix inverters that MATLAB already has. We want you to use the ones that you built.
Oh, wait, did you say that earlier? I didn't see it.
Yes.
Sorry.
Right here, second paragraph. So we don't specify the P inverse, but basically any of the matrix inversion functions that MATLAB has. We want you to use the ones that you coded. So once you have the pseudo inverse, we want you to calculate W for the best ellipse. So that W basically means the best ellipse. That's the one that describes it. All right. Then we want you to plot the provided points as a scatter, we give you here the specifications. We want the markers to be X's. We want the color to be blue. The size, that's up to you. We are not specifying it. In the same graph, we want you to plot the solution that you got with my Gauss solver. We give you the plotting specifications here. And in the same graph also, the one you got with my LU solver. Here are the specifications for plotting. Remember, you will have to do a presentation of this project. So we want you to time the solutions by using my Gauss solver and using my LU solver, and briefly comment on that. There's nothing more that you need to do. Just time them and tell us what you learn. And also make sure to label the both solutions in the plot as Gauss solution and LU solution. Also, in case there are any questions, if you're wondering what do I mean by the solutions you got by my Gauss solver and the solution with my LU solver, you use both of those functions to calculate a pseudo inverse for phi. So basically, save one pseudo inverse with my Gauss solver, another pseudo inverse with my LU solver. That those two will give you a W with my Gauss solver, a W with my LU solver. So you have two W's. So basically, you have two ellipses. We want you to compare them. And yeah, that's basically it. Also, plotting those two. So once you have the W for your best ellipse, plotting those is not a trivial task, because this is still, so what we are doing this by turning all these polynomials into a matrix and doing the inverse that I show you below. This is called linearizing a problem, because you end up with an expression like this: phi times W equals something. So this is a linear problem. But although we linearize it, this equation over here, the equation for an ellipse, this is still a nonlinear equation. So even if we know the W's, plotting these guys is not trivial. So we basically give you the code to plotting. Yeah. Look through the code. You basically only need to copy and paste this and adjust it such that so there's a okay here. There's this variable W here. You will adjust this to whatever you call your W from my Gauss solver and the other W from my LU solver. That's the only modification you need to do to this code, and yeah, whatever you need to do it to make it plot in the same graph as the scatter plot. But don't worry too much about the plotting. We give it to you. At the end, we want you to provide us with three things: the my Gauss solver as a function, as its own file, my LU solver as its own file, and the regression problem that we just described as its own file. All of them on a zip. And again, there's a presentation. When's the presentation date, Dennis? Dennis?
Sorry, repeat that.
When's the presentation date?
It's good question. It was Thursday, I think. Thursday 3 is 6. Let me check the calendar.
So this Thursday?
No, 17th of December. Okay.
Okay, that makes more
17th
sense.
of December, Tuesday. No, Thursday 3 to 6. Y'all can confirm on Cal Central. It should be like the final time for E7. It's just the final date. Unless you guys like talk with Mia Jose and then schedule a different time slot.
Okay, so regarding the project, it is not trivial. It is not trivial. Understanding it take uh, will take a while for you guys to go home, look at the presentation, look uh, at the PDF, and try to find a pseudocode. You are working in groups. Try to figure stuff out within your groups. Like, don't try to solve this all on your own. That's great, but you don't need to. So please use the fact that you have a group. And well, yeah, that's it. It's not trivial, but once you find out exactly what the logic is, it's really not that bad to code. Like, it should not take you more than 100 lines each function.
And if anyone has trouble like getting in touch with their groups, let me or Jose know.
As soon as possible, I would recommend, because again, coding this is not that bad, really, but understanding it's not trivial. So I would not waste time. Okay.
The
Also,
groups are
everyone-
just so that we have people to. Oh, I'm sorry. Go ahead.
You can go.
I was just asking. So the groups then are just so that we have other students to talk with us about, though, right? We're all submitting our own programs and everything, right?
I believe it's one per group. It is actually a group project.
Yeah, it is actually a group
Okay.
project.
Oh, okay, got it.
And Jose, I wanted to also talk with you. We should probably, since each presentation is going to not take up the entire time, that I was wondering if we wanted to schedule people for like a common, like, let's say we have 3 to 6, right? Let's say each one takes 15 minutes. I'm not sure how long they're actually going to take. Let's say like one group goes 3 to 15, 3 to 3:15, another goes 3:15 to 3:30. We can schedule it like that so that people only need to come in at their scheduled time slot and not stay the whole time to wait for, they go first or they go second. Or do you want to randomize it?
I think, how many groups do we have? We have only 4 groups, right?
Right.
Only 4 groups.
Yeah, 4.
Honestly, I would aim for your presentations to be 5 to 8 minutes. Yeah, you don't need to do anything very fancy for the presentation. Just show us what you did, tell us what you learned. If it didn't work for some reason, show us how far you got. And yeah, the presentation should not be something fancy. So I think we should be able to go through the 4 groups in something like half an hour. So
Half an hour. Okay.
yeah, yeah, I don't.
No scheduling. Come in for that half hour.
Yeah, I think that would be easiest. I also know that you have a lot of stuff to do right now. It's the end of the semester, so I don't want you to spend a lot of time on the presentations. We don't need anything too fancy. We just want to see what you did. On that
Would it be
note,
accurate to say it's just an informal presentation?
sorry?
So it's just be an informal presentation. Like, we're not going to ask them any like
Yeah.
hard questions.
Yeah, no, absolutely
Okay.
not. Absolutely not.
Who's your least favorite group member?
On that note, if your program is not working, if your functions are not working, contact us early. Like, this project is meant to be challenging. Like, we want you to actually think through it, but yeah, it's not impossible. It's not a weeding mechanism. We're not trying to give you a bad grade or anything. Like, reach out.
Who's George?
Speaking of the groups, where can I find the Excel sheet that lists all the groups?
It should be the same one that we use for the question. Okay, I also posted it in the recording for last Monday, I believe, like the link to the groups and everything. I can repost it here. Here.
That would be great. Yeah, thank you.
Yeah, I'm pretty sure that's under the recording. I like put it in the description for. I didn't tell anyone, but like it's in the description for last Monday's recording, which I should probably link that here as well.
Also, I probably should stop the recording right now.